Okay, everyone. So B6, technically back up a little bit. B7, we're going to get caught up to the same place. But let's kind of review what we learned last class, and then we'll transition into the new stuff. Now, in this lesson today, I know I'm not physically with you, so take the best notes that you can, try all the problems, but then after fall break, we can clarify any questions that you may have with each other, okay? So, all right, here we go. So last time we talked about this idea of calorimetry, where calorimetry is the experimental procedure for figuring out the heat, right, or the energy that's lost or gained during reaction. So we were doing this problem, if you go back to problem 5.5b, okay, and we found in doing this problem that Q for the solution was 2.7 times 10 to the third joules. So this tells us that when I reacted 50 milliliters of both, that's how much heat the solution absorbed. Now, the question wants you to know, calculate the enthalpy change for the reaction. So two things have to happen in order to get enthalpy. So remember that enthalpy is delta H. So the delta H for reaction is we're going to take the negative Q of the solution divided by the moles. Now the reason why it's a negative Q is because if the solution released this much, then the Q for the reaction would be the negative value of that. Because if the solution released it, then the reaction, sorry, I said that backwards. So if the solution absorbed this much, because it's positive, then that means the reaction actually released it, which if you notice, the Q of the reaction sign should match the temperature change, which it does, because we said that it should be XO. Okay, so we take, you can think negative Q, or if it's easier, just think that the Q of the reaction, and then divide it by the moles, and you have to focus on whichever one is limiting. Now, in this case, we have 50 milliliters of both. It's a 1-to-1 ratio when we write out the balanced equation. So there is no official limiting in this case. So whichever one we pick is fine. But notice the difference that this is based on the limiting moles. When we did the mass earlier, that was the total mass, okay? All right, so to find the limiting moles, since we have molarity and we have volume, we can convert our volume into liters, so it's 50 milliliters, so that would be 0.05 liters, which if I times that by the molarity of 1, we get 0.05 moles. Which then, if we plug them both in up here, and now it's going to be negative divided by 0.05. This will give us the delta H for the reaction. Now, the thing about the delta H, once again, is this is constant for the reaction. This tells us the ratio of heat in relation to how many moles are being used. The Q simply tells us how much heat was produced when we reacted 100 grams. Okay, so calorimetry is the experimental process of finding delta H. Okay, all right, so now the other way, so this is another way in which you can calculate a delta H. And this goes back to my silly bonus question from last time with my house and traveling to mountains and things like that. So in the silly bonus question, it is very straightforward that in order to figure out how to get from A to C, you knew how far A and B was, and you knew how far B to C was, and so you could just connect it all together. Hess's law is the same idea, and it can really be that simple. So that's why I did that bonus last time, was to hopefully help you recognize how simple Hess's law can be. So the idea of Hess's law is if I know the steps of a whole reaction, I can look at all those steps to figure out the total energy lost or gained by a reaction altogether. Okay, so let's look at exercise 5.6a on your practice problem set. Okay, so it tells us the enthalpy of combustion for C to CO2 is negative 393.5. So this was determined experimentally. Okay, the enthalpy change for the combustion of CO to CO2 is this. also determined experimentally. We're trying to find the calculated data for the enthalpy of this reaction. So this is our goal. Think of these as like our different steps to our destination. Now, what we need to make sure we look at is making sure that the steps line up like they should, right? So like with our little silly question last time, there's a lovely picture, okay? If you know A to B and you know C to B, right? C to B is obviously the same distance as B to C, and so it's the same amount. Same thing applies here. The difference is the negative and positive sign change of our delta H. Okay, so looking at this is your goal, okay, you need the steps to add up to this. So the first thing I pay attention to are the position of things based on the arrow. So I noticed that, okay, carbon is a reactant in the goal equation. Oh, good. And in the first step, carbon is a reactant, so that's in its right spot. Now, I noticed that, oh, CO is a product, but in the second step, CO is a reactant. So we need to look at the second step in reverse. So let's take that second step and rewrite it. So we're going to have CO2, and I'm going to try to keep my arrows lined up with each other. And then we have CO plus 0.5O2. And I'm going to scribble this out because I rewrote it. Okay, that puts my CO on the right side of the arrow where it needs to be. Now, since I flipped the reaction here, that causes a sign change. So we change the sign when reaction flips. Same value, just different direction, just like going down the road a different way, okay? All right, so now, since everything in its right spot, what we're going to do is we're going to add it up together. Now, kind of like when we did spectator ions, if you see something that appears on both sides of the equation, you can cancel it out because it's really not there anymore. So if you notice, the CO2 is a product in this reaction, and then it's a reactant in this reaction, so we can cross it off. Now, the other thing is you'll notice that there's an O2 on the left and a 0.5 O2 on the right. So it kind of cancels out, but not all the way. So this is all gone, and now there's 0.5 left of this. Then, once you cancel out the things that are the same on both sides, you carry everything else down. So we have carbon plus 0.5 O2 changing into CO. Now, once you get to the point where, when you add them together, it equals the goal reaction that we are trying to achieve, to find the delta H now, we simply just add the delta H's together, taking into account the sign change that occurred. Okay, so we add those together and get a final answer for the delta H of our combustion. So I got negative 110.5. And that would be your final answer. And that's the idea of Hess's law, is you rearrange steps so that they can add up to what you're trying to achieve, and then you can add up the delta H's. Okay, let's try another one. So let's look at 5.6b. Okay, so 5.6b, also using Hess's law. Okay, let's get rid of all this. Okay, so this right here is the goal that I'm trying to find the delta H for. Right, so we want to know the delta H for this reaction. And these are the steps that it gives me that I'm going to try to add up to that thing. So once again, the first thing that I do is I make sure everything is arranged the way it needs to be arranged. So right off the bat, I see, oh wait, C2H2 is a reactant, but in this, it's a product. So I'm going to rewrite this step in reverse. Okay, so we're going to have H2O plus 2 CO2s changing into C2H2 plus 2.5O2. Okay, and then that's going to make my delta H for that reaction change sign. Okay, I'm going to scribble this out since we reversed it. All right, check the placement of other things. So it looks like, yep, carbon needs to be a reactant, so that's okay. Hydrogen needs to be a reactant, that's good. Okay, now notice though something else in this one. So in my end product, I need 2 carbons. I only have 1 carbon on the left side of the arrow, even if I add them all together. So what that means is I'm going to take this reaction so that it can match here and times everything by 2. So we're going to put a 2 there, a 2 there, a 2 there, and then times this by 2. Because as long as, like in math, as long as I do it to one side of the equation, when I do to the other side, you'll get the same answer. Okay? All right, I think everything now matches piecewise up here, so now let's add them together and see what cancels out. So remember, if something appears the same on both sides, then it cancels out completely. Otherwise, it just will reduce it down. So I see, all right, I see an H2O here and an H2O there, so those cancel. I see 2 CO2s and 2 CO2s. And then I see 2 O2s and 2.5 O2s, and then there's also a 0.5, so all of the O2s cancel out with each other. So now let's rewrite what's left. So I have 2C plus H2, changing it into C2H2. So I just carry down the things that didn't cancel. I then check to see, does this match what I was trying to get? And it does. So now I can add up my new delta H's. Once again, timesing this one by 2, flipping the sign of the first one, and we get 226.8 kilojoules. Hess's law. Okay? If by chance you get to this step and this reaction that you added together does not match here, you need to go back and manipulate these to get here. Okay? And one of your homework assignments tonight is going to be practicing a lot of stuff with Hess's law. So hopefully it will help you get it down a little bit better. I'll also post an extra video on the website of just more information about how to do Hess's law. So if you're confused about it, you can also watch that video to get more help. Okay? All right, so the third way, so the first way to find delta H is using calorimetry. The second way to find delta H is using Hess's law. Now the third way to find it is a variation pretty much of Hess's law in a different way. So the third way is to use these things known as enthalpies of formation. So an enthalpy of formation, if you look up there at the symbol, is delta H, which is enthalpy. The F is for formation, and the naught is telling you you're at standard state, okay, under standard conditions, okay? What an enthalpy of formation is it is telling you the reaction for the simplest way of forming something from just its products. So for example, the enthalpy of formation for CO2 would be carbon plus oxygen makes carbon dioxide, right? And then the enthalpy would be how much heat does that process take. Okay, so enthalpy of formation is referring to breaking down things into their simplest of elements. Once again, for example, for glucose, it would be carbon plus oxygen plus hydrogen making glucose. Okay, so it's things down in their simplest form of how it's made. Okay, now the thing about these enthalpies of formation is they have pretty much been calculated for so many things out there. So the sum we'll give you here in just a second or maybe actually pause the video sub and pass out the paper that looks like this. Okay? So this paper on here has a few different columns. So the one we're focused on right now is the delta H F one. We'll learn about delta G and S in another unit. Okay? But what this is it tells you the enthalpies of formation for all of these different substances. So when you're given this data, or you have this data available to you, the other way that you can calculate enthalpy, so we're going to skip that question, is using this reaction. So if you go to, I believe it should be on page, the very last page, so page 7 of your notes, this equation is written in for you. So what this equation means is the symbol, this one right here, is called sigma. It's a Greek symbol, and it means the sum of, and then N and M are the stoichiometric coefficients of a chemical equation. Okay? So this equation is a third way that we can find the enthalpy for a reaction. So let's go to a problem and try it out. Okay, so go to exercise 5.7b. It says calculate the standard enthalpy change for the combustion of 1 mole of benzene, which is C6H6. So this is a way in which we can calculate the enthalpy change for benzene without actually going into the lab and doing it. Now, in doing this question, this table of values were supposed to be printed on your paper because they are something that would be given to you. You don't have to memorize enthalpies of formation. That would be ridiculous. Okay, so our equation said that we need to take the sum of the products and minus the sum of the reactants. So to find the delta H for this reaction, we need to take the sum of the products minus the sum of the reactants.
All right, everyone. So my GoPro memory card got full. And so here's what we're going to do the last problem. Okay, so follow along with me. So the equation tells us that we're going to take the sum of the products minus the sum of the reactants, taking into account the mole ratios. Now there's a few slight errors on this question. First off, it's not correctly balanced. There should be a 15 halves right here. And then the other issue is on the slideshow, it has this as a liquid, but it should be listed as a gas. That actually would change the delta HF that we would use. Because notice that this one is for water as a gas, not as a liquid. And if you look on the chart, the sub gave you the delta HF formation for being a liquid is different than for a gas. So pay close attention to those subscripts. Okay, so the outline for the equation goes like this. Is we're going to take the sum of the products. So our products are CO2 and water. So since we have 6 CO2s, we're going to do 6 times the delta HF formation for CO2 plus 3 times the delta HF formation for H2O. These are my products. Okay. Sorry, apologize. Okay, so then we're going to take the products and we minus from the reactants. So we only have one C6H6, so we're just going to take the delta H of formation for that compound. Then we would take plus 15 halves times the delta HF of O2. Now, I wrote this all out just so you could see where everything was coming from. You don't need to do this step, you can just plug your values in. So let's do that now. So we're gonna do 6 times the delta HF formation for carbon dioxide, so negative 393.5 plus, so multiply those together, 3 times the delta HF formation for our water, 241.9, and then minus the delta HF formation for our C6H6. Now you may notice in our chart here that we do not have a delta HF formation for oxygen. the thing is, remember that delta H formation is the formation of something from its elements. And since oxygen is an element, it doesn't have other elements to be formed of. And that will actually apply to all things that are just in their elemental form, that their delta H of formation will just be 0. So technically, if we were to write it in, it would be 15 halves times 0. Pretty good idea if it's not listed in the chart, but it's in your equation. It's because it's just an element, and so it should be 0. Then you would plug that all into your calculator and get a final answer. So I got a final answer of negative 3,170 kilojoules per mole for the delta H of reaction. So what I'd like you to do is flip your notes over, and let's just summarize real quick the 3 ways we just talked about for calculating delta H for the reaction. So on the very back of your notes, it's just a blank piece of paper. So let's just do a quick summary of the 3 ways to find delta H. Okay? Okay, so first way that we talked about was through the process of calorimetry. Okay, so in calorimetry, the thing that would be given would be experimental data. Okay, so if you were given experimental data about mass and temperature change and specific heat, that is a sign that you're going to use the process of calorimetry, which means we use Q equals MC delta T. And then from that, we can then find our delta H for our reaction, right? Because remember that delta H for reaction is Q of the reaction per mole. Okay? Second way in which delta H can be found is through Hess's law. Okay? So with Hess's law, the thing that would be given is enthalpies of reactions. From those enthalpies of reactions, you would rearrange, right? Flip the sign, times by 2, so on and so forth, and add together. Basics of Hess's law. Now the third way that we just talked about is where you can use the equation of products minus the reactants. Okay, and in doing the products minus the reactants, the thing that would be given would be delta H of formations, right? Key thing. If those are given to you, then you can use that equation, which that technical equation is on your formula sheet, so you don't need to write it down, or I guess you have it written down, but you don't have to have it memorized. So yeah, so those are the 3 ways in which we can find delta H. Once again, take note of the questions that you have from today's lesson so we can address them next time all together. Your homework assignment that you're going to work on now is about practicing Hess's law. So you can work on doing that with one another. The answers are posted on the website, so you can make sure you're doing it correct. And then the other thing that the sub's going to pass out to you is a practice assignment of a bunch of free response questions from old tests that deal with topics from chapters 4 and 5. So this should be an opportunity for those of you that struggled a little bit with the free response on the last test to get some good practice in of a lot of different kinds. What I am requiring of you is that when you come to class next time after fall break, at least 50% of these free response questions have been answered. So just 50% of them need to be answered by the next time you come to class. All right, good luck, everyone.